Hello everyone. We're going to get started in just a minute. If you have any questions from last time, you can put those in the chat, and I'll try to deal with maybe some quick questions before we start. Otherwise, we're going to start Chapter 11 stuff today, which the first question is about. Hopefully you have seen the video, the pre-class video. Otherwise, you're going to be a bit confused. So hopefully you've seen that and have some idea of what's going on. Nice haircut. Thank you. I traded the painting for a haircut. That was my my move. Okay, it looks like most people have answered the top hat. I'm going to close it and see what you guys said. So we are looking at this graph of the function 10 minus x. And what I have is exactly what's going to happen. I have it in Desmos. So really this question is predicting you have this graph 10 minus 2x, which is a slopey line thing. This represents the temperature in a bar of steel, and when I hit this play button over here, it's going to animate it and it's going to show you what happens. So I've solved it already. So the question is, can you guys predict what will happen? And I'm going to hit play and let's see who is right. So what were the options? It was like going to 0 uniformly, going to 10, going to 5. Let's see what happens when I hit play. Look at that. So it looks like it eventually goes to 0, but the first thing it does is it goes up. So on the left side of the bar of steel, it goes down almost right away. Let's play it again. So if we take this time slider, it starts at 10 degrees on the left side. Almost immediately that goes down to 0. But let's see what's happening on the right side. On the right side, it starts at 0, and the temperature actually goes up first. So the temperature goes up and then down. So something sort of complicated happening. So let's see if you guys were figuring out what that was. Okay, already opened this. Let's see the responses. Most people think the entire bar approaches the average temperature of 5 degrees, and that is wrong. So that is not what happened. The bar eventually went to 0, but even option A was also wrong, because it didn't go to 0. It didn't cool down everywhere. First it heated up at the end, and then it cooled down. So what the hell is going on? The next question is about that. 9% of people figured out that actually I didn't tell you enough information to see what was going on. So the reason there was something sort of complicated and crazy going on is because I left out some information in the write-up. So if somebody tells you what the temperature is initially of a bar of steel, that is not enough information to know what happens. And I was missing an important piece of information. So that's what the next question is about. This is the link to the Desmos, by the way. You can open it up and play with it yourself if you want. So you just copy and paste that link. And then you use the S slider. So the slider S means time. You can't use T in Desmos because it's reserved for something else. So if you just hit play there, that'll do the slider. Okay. So what was missing? That's the next top hat question. What was missing? The missing information, which is needed to determine the temperature function, are the blank blank. And you have to tell me what blank blank is. So you should have an idea of what this is from the video the other day. Okay, maybe while you guys are doing this, will this work? Let me see if I can go back to the animation here. Is that still open in this meantime? Yes, okay, good. So question's still open, but I'm in the, can I make this visible to students? Oh, this is exciting. Okay, should probably use that more. Okay, yeah. So if you want to see what's going on here, once again, really weird stuff. happening in this bar of steel. Okay, how are we doing on the blank blank? 78 out of 89 people answered. Okay, most people have answered. I'm going to give you 30 more seconds or something. So if you're the last 6 people and you haven't answered yet, put something in. Take a guess. I guess if you want to talk to people in your Facebook chat or something, figure out what you think the answer is. That's totally legit. Okay, most people are in. I'm going to stop the question here. Here we go. Let's see, what did people say? Most people are saying the boundary conditions. Some people are saying the boundary values. This is the boundary condition. And do I have a correct answer here? So boundary conditions is the right answer. Boundary condition, well, there's 2 of them. There's one on the left and one on the right. So I guess, that's pretty close. Boundary value is also very close to being right. The reason it's a boundary condition and not a boundary value is that sometimes the boundary condition is specifying something that is not just the value. So sometimes a boundary condition is the boundary value, but not always. So that's why we want to say boundary conditions. And that is the thing that is missing. So this week, or for the last little bit of the course, we're doing the very last topic, which is PDEs. And the thing, if you're going to remember one thing about PDEs, is that PDEs are an equation plus boundary conditions, and that is just as important. We didn't have that in ODEs. So for PDEs, we have an equation plus a boundary condition. Usually there's more than one. There's usually a left and a right. And very few problems there's just one. So by an equation I mean something like ut equals alpha squared uxx. That's the equation we're working on today, which is the heat equation. I also want to remind you what these t's and x's mean. These are partial derivatives. So the p stands for partial. So sometimes people write it like this, u sub t equals u sub xx, but sometimes people also write it like this, partial u alpha squared partial x x u, or even something like this, partial t, u is alpha squared partial x squared. These are all mean the same thing. They're just different notations for the same identical thing. Most often people use this one because they are lazy. This one's easy to write. Okay, so if you have an equation plus boundary conditions, you can get a general solution to your PDE. And then if you take the initial condition, so the general solution, just like in everything else we've done, is going to involve some constants, C1, C2. And if you also have an initial condition, you can take the general solution, mix it with the initial condition, and get a specific solution. So the thing that people often forget is the boundary conditions. Without the boundary conditions, you cannot find a general solution. So that is an important new piece of the puzzle. Other than this new thing with the boundary conditions, everything we've learned about ODEs from chapter 3 onwards, so like second order equations, 2x2 systems and stuff, we're going to do all the same tricks. So it is different because it's this partial derivative thing, but really it's using the same kinds of things as we're doing before. And I'd say the other ingredients are the things from chapter 10 that we just did. So the things from chapter 10.2, which is Fourier series type things, and from 10.3, which is these eigenvalue problems, our eigenfunction problems rather. So These two ingredients are going to be used, but other than that, the actual equation-y part is going to be extremely similar to the other things we've did. So hopefully you won't find it super confusing. If you understood all these individual pieces, I think it's okay. People get really scared of PDEs, but I think part of the complication is it's just a lot of different parts. So this will be a part, this Fourier series stuff, this eigenfunction thing will be a part. You're going to have to remember tricks like we used from chapter 3 and so on, and every individual part kind of you have to solve separately and then put them all together. So it can be a lot of different things to put together, but each individual part hopefully makes sense on its own. That's what we're going to be doing today. I want to talk a little bit more about the different boundary conditions because they're really important for PDEs and they really tell you what's going on. So I have a couple more questions about boundary conditions for you guys. This one is a fill in the blank. So here are two possible types of boundary conditions. In one of them, you set the value to 0, and in one of them you set the derivative of the value to 0. And these two different types of values represent different real-life type things. So two possibilities for the boundary condition at x equals 0, and I made two blanks there, so hopefully you can fill in two different blanks on your top hat and tell me what these mean in real life. So you're translating from math to real life. So I'll give you a minute or two to work on that. Maybe I'll start a timer here. And you should have seen these vaguely in the video before class. Yeah, so I'm assuming you have a little bit of familiarity with these boundary conditions and like what they are, roughly speaking, from the video. And we'll see how much you guys can get to these two questions. Again, feel free to ask questions in the chat. Okay, so I think most people have something in. There are a couple of good questions in the chat here that I will address in a sec, but I just want to see how you guys are doing. First of all, I'll open it and see how people are doing, and then I will reopen it. So just to remind you, in case you're super confused about what these boundary conditions are, a boundary condition tells you something about what the function we're looking for is doing. So a PDE is a partial differential equation. We're looking for a function utx, is the unknown function. Unknown function. So the thing that's new is that it's a function of two variables, t and x. By the way, I'm always going to use t and x. I think the textbook might use x and t. So don't get thrown off by the order. Whichever one has the t in it, that's time, and the one that has the x in it is space. Okay, so we're looking for this unknown function, and a boundary condition tells you something about the function. What does it tell you? It tells you something that happens at x equals 0 and for every time t. And so that is what option 1 in the top hat was saying. So it's saying, look at the condition ut 0 equals 0. That means at position x equals 0, the function we're looking for, the unknown function utx, always equals 0. So that's what it means mathematically. The function is always equal to 0. And that has an interpretation in real life. And what I'm asking you to do is fill in the blank with what that is. So let's see what people said for the first one. I think I can just show the first thing. which represents keeping the left end of the bar constant. Keeping it constant. Keeping what about it constant? So there's something we're keeping constant. What is it? Same with 0. So there's something about it that's 0. It is at 0. Yeah, so we're talking about position at x equals 0. So I would say at 0 is not enough on its own. Some people are saying cool. So some people have other ideas. So I'm going to reopen it. Ooh, isothermal. That's a fancy word. So you gotta, maybe you can read some of these. You can chat with people if you have a Facebook chat or something, or we can type in the comments if you have an idea. Some of these are on the right track. Some of them are not on the right track. Constant and 0 are also good, but not specific enough. So I'm going to reopen it, and you guys can try to tell me again, what do we think this means? And I'm going to also write some things on paper here. So this is all times t. So this is ut0 equals 0. So we're talking about keeping the function u. It's always equal to 0 at x equals 0, no matter what time is. That's the first boundary condition. Okay, I have only a couple seconds left here in Top Hat. Maybe I should open that back up. Let's see if the answer has changed. All right, this is great. So people have changed from constant to constant temperature, which is fantastic. That is what is going on. So constant temperature is definitely a lot better than constant. People who are still on 0, 0 is not specific enough. So what is going on here? Remember the function utx is supposed to represent the temperature at time t and at position x. So if the boundary condition says ut0 at x equals 0 is always 0, and that represents the temperature at time t and position 0, this mathematical thing, keeping the function at 0, is the same as keeping the temperature of the rod at position 0 to be equal to 0. So I would say constant temperature is on the right track, but it is not specific enough. I would say what you need to say is it's constant temperature and the constant is 0. So we're taking the rod and we're keeping one end in ice so that the temperature is always 0. So I think people who said at 0 degrees or at 0 temperature is right. Just saying 0 on its own is not enough. Like what is 0, right? You got to make sure you are keeping track of the things that are going on here. There are sort of 3 different units going on, right? There's time. In this thing, this is time. This is location or space. And this 0 over here is temperature. Temperature. So you got to make sure you say what these are. And what this represents is keeping location 0 at temperature 0 for all time t. That's what's going on. Okay, so that is the first blank. The first blank. Can I show you who's correct in this one? Yeah, so at temperature 0 is what I wrote. So if you wrote something like that, like at 0 degrees, at 0 temperature, that's also correct. Some of them are close. Constant at 0 degrees, that's good too. There was a really good comment in the chat a minute ago, which somebody said, what if, oh, by the way, I'm looking at Top Hat, I'm looking at Top Hat answers. So I said at temperature 0, some people were right, some people were not. Someone in the chat wrote, what if the initial temperatures are such that it's not 0 degrees at x equals 0? I think that's a really good comment. So I'm gonna answer this question right now. What if, let me copy it out. Answer 2. So there's 2 things that I want to say about this. What if the initial temperatures are such that it's not 0 degrees at x equals 0? So one thing is, we're not talking about the initial temperature here. So the initial temperature would be what is going on at t equals 0. That would be like an initial condition. What we're talking about right now are boundary conditions, and those happen for all time t and at x equals 0. So we're not talking about what is the bar initially doing. We're talking about how are the ends of the bar maintained throughout time. So we're not talking about initial temperatures. We're talking about boundary conditions. And the question is, what happens if it's not 0? You can set it to any value you want. So a different boundary condition, would be u of t0 equals 7 at all times t. So this is, again, at x equals 0. And what this would represent is keeping one end of the bar always to be constant, but the constant is now 7. So you can totally do that. That's a different boundary condition. It's not listed on the ones I gave in the top hat question, but it's a totally valid boundary condition. The reason we're doing this one first is this one is a homogeneous boundary condition. This one is homogeneous. And this one is non-homogeneous. And we're going to do non-homogeneous stuff in chapter 11.2, which is next class. Today we're only going to do homogeneous things. And just like in ordinary differential equations, it's easier to first do the homogeneous things and solve that, get that going. And then once you have the homogeneous things figured out, you just have to add on the right things to solve for this one. So that's why this was the one we're going to focus on, the homogeneous one. And then we're going to do these ones next time. But you can put any constant you want. So people who wrote in the chat, who wrote constant temperature, you can do a constant temperature boundary condition that is not 0, but the one I gave here in option 1, ut0 equals 0 for every t, that represents keeping it at temperature 0. Okay, that was number 1. I'm going to move on to blank 2, which is something about this funny squiggle x thing. So we'll see what that means. It's a good chance if you want to ask a question about the first type of boundary condition and what it represents. Okay, so, feel free to ask questions anytime. Let's see what you guys wrote for blank 2. Blank 2. Oh, it's revealed. Oh, no. Oh, no. Okay, maybe you didn't see that. Let's see what people said. People wrote constant temperature. This is mostly wrong. So the second one does not represent a constant temperature. It doesn't really have anything to do with constants. Hot, fixed. So I gave a hint by showing you the answer for a second, so if you were paying attention in the stream, you'll know the answer. I'm going to reopen the responses on top hat one more time. See if you can come up with what blank 2 represents. So again, probably if you haven't seen the video or don't remember from the video, this will be a tough one. But try to think what it means or what it could mean in terms of the interpretations we have on this page. And let's, try to get on blank 2. Okay, let's do that for another minute. Okay, there's 30 seconds left on the top hat for me. Yeah, I guess you don't need to see the question. Let's look at the paper. There's like 10 seconds left, 5 seconds left, something like that. Okay. What did people say in blank 2? Insulated. Lots of people said insulated. That is what I had as the right answer. So you maybe saw that and copied it. So isolated. Isolated is also good. So changing steadily. Flat slope. I like that, flat slope. So flat slope is describing what's happening mathematically. That's for sure. So flat slope is a good way to say it. So let's do some paper over here. So saying the function has to be 0, we know what that means. It means the function is always 0 at 0. But saying its derivative is 0 means that the function is flat. So mathematically, partial x ut 0 equals 0, this means the function is flat at position x equals 0. So if you drew a graph of the function, it would look like that. It's something that's flat. Okay, that was a bad picture. Let's try again. It starts out flat, and then it might change afterwards. And the thing is, it's not constant. So it's flat, but it can go up and down. So being a constant temperature would mean you can't move. You're always a constant. That's not what's happening. It is flat, so it can go up and down, but it's always flat. What does the flatness have to do with anything? Well, flatness in the temperature profile, remember this is position, and this is temperature on this axis. So being flat means that if you look at the bar, one end of the, like a little piece of the bar is the same temperature as a little bit that way. And that means there's no temperature gradient in the bar. So that's one way to say it, is there is no temperature gradient. And when there's no temperature gradient, the physics of heat mean that heat flows from where it's hot to where it is not hot, from where it's hot to where it's not. And so if there's no temperature gradient, there is no heat flow. So because of physics, no temperature gradient is the same as no heat flow. And this is what happens if you have an insulated end. So if you put an insulator at the end of the rod so that heat cannot flow, that will cause no temperature gradient, because heat flowing happens exactly when there's a temperature gradient, and that is exactly this boundary condition with the derivative. Okay, so that is boundary conditions. These are the two types of boundary conditions we're going to look at. So this one is boundary condition type 2, and this is boundary condition type 1, and those are the two we're going to work with today. Somebody in the chat says, what if the question was asking about a partial with respect to time? So a partial with respect to time is not a boundary condition. So a boundary condition is always going to involve the function and its x derivatives. So I can show you a little graph of that. Actually, let me see if I can get it straight from the textbook. So normally I reference the textbook and can't do anything, but because we're on chat here. Okay, yeah, the textbook, I'm not sure if it has a good picture of this or not. I'll draw my own crappy picture for you. I think the textbook has a picture of this in chapter 11. So if you want to think about the possible places we're solving, we're sort of solving in a domain like this. So we have from 0 to L in x, and we have all possible times. So this is time t. So this is time and space. So this represents the domain that we're solving for. And we want to solve for what is the function going on. We want to solve here. We want to solve of u tx in here. And what we are given is we're given the boundary conditions which tell you what's happening on the two ends. So at x equals 0, at x equals 0, and at x equals L. So these are boundary conditions for these two things. And they're at x equals 0 and for all times t. So it's sort of this vertical line here and here. We're also given an initial condition, which is this thing. So that's the initial. So if you want to think about it this way, we have this domain, which is x going from 0 to L, where L is the length of the bar. Time is anything, and we're sort of given data about what the function does on the outside of this thing. And the boundary conditions are the two sides, and the initial condition is the bottom. And then we take that information and we solve it, and we solve to get the whole value of the function. So the thing about having a time derivative is sort of along the boundary. So since the time direction is this way, having information in the time direction would be no good for the boundary conditions, because it sort of doesn't point to the interior. So for the boundary conditions, we want to have either the function u or its derivative, like this. Yeah, and that gives you information about this thing on the two sides. The initial condition is not so exciting. It's just we're telling you what the function is. So that one's not so complicated, and it's not new. We've seen that lots of times before. But the two sides, the two boundary conditions, that is sort of the new thing here. Okay, so I'm not sure if that satisfies you with that question. Yeah, so the time derivative doesn't for a boundary condition is not a valid boundary condition and doesn't represent anything for this problem. Okay. So those are the two types of boundary conditions. I think I have some screenshot from the textbook here in Top Hat that you can look at. So the textbook says, you know, if you have them equal to 0, that's a fixed temperature at both ends, or you can insulate the ends and the derivative is 0. There is a third exotic type, which is this funny thing with Newton's law of cooling with an H1 and an H2. You can also read about this one. We're not really going to be doing this one. So this one is sort of complicated, and you get a lot uglier functions. The first two are the ones we're going to focus on. So if you can understand the first two very well, you're golden. Don't worry about the last one. So that is the thing that's going on here. We have the heat equation, we have boundary conditions, and we're going to start solving it in a minute. I'm going to open it up for questions here, if you have any, in Top Hat. So hopefully you've seen the video, you kind of know what the heat equation is supposed to be doing in the first place. We're going to get into the nitty-gritty math stuff starting in a minute here. Okay. What happened to the painting? I traded it for a haircut. That was what happened to the painting. It's a bartering system. What part of the textbook is it? That is a very good question. So we're doing chapter 11 in the textbook. Chapters 10 and 11 are not in the bound copy of the textbook. So what you have to do is you have to go and download chapter 11 from the publisher's website. So they made the chapters 10 and 11 are free, and you should download them. Chapter 10 is kind of not that great, and that's why I gave out notes and things. But chapter 11 is actually pretty good. It's like not terrible, and it's mostly readable. And I'm going to be following it pretty closely today. So I'm going to be doing like examples 1 and 2 from chapter 11.1. So it's good if you have that to follow along. You wanted the page number? I don't know. It's like the third page of chapter 11. Does it matter if the temperature is Celsius or Kelvin? That is a great question. What's the difference between Celsius and Kelvin? There is a shift there. You're adding on a constant. So the answer to the question, does it matter if it's Celsius or Kelvin? The answer is going to be, how does the equation behave when you add a constant to it? And that is going to be answered when we do non-homogeneous problems. So when we learn to do non-homogeneous problems, like when I said we're going to do this one next time, u of t0 equals 7, the difference between these two things, 7 and 0, is exactly the difference between Kelvin and Celsius, so we're going to learn how that happens next time. So for now, I guess pretend it's Kelvin. No, we don't want it. It should be allowed to be negative. So let's do Celsius. Let's do Celsius for now. And we'll learn the difference next time. Okay. In this course, do we consider external cooling to the whole bar? That's another great question. We are also going to do that next time. So for now, the bar only has things happening at the end, nothing happening in the middle, except for heat flowing in between the bar. So the bar, there's nothing touching the bar in the middle of the bar except for at the two ends, and we're going to learn how to do that differently when we do the non-homogeneous stuff. So the non-homogeneous will have different things. People want to know what actually happened to the painting, and I'm going to leave the mystery alive and not say. In this course, do we consider external cooling? All right, answer that. Can we say if the ends are at constant temperatures, then they are insulated, because the partial derivative would be 0 for a constant temperature? Oh, this is a good point. Okay, look, this is great. This is good. So somebody is thinking about this stuff, and you're saying, this is a good point. So if they're saying, look, man, if you're telling me u of t0 equals 0, this is the constant temperature 0 boundary condition. If it's always 0, then the derivative is 0, right? If something is always 0, that means it's not changing, so the derivative is 0. But there is a problem with that, is when you say the derivative, you got to be careful about what derivative you're talking about. So the time derivative is 0. It's not changing in time, it's a constant in time, but that does not mean that the space derivative, which is this thing, partial xu of t0, this is not equal to 0. So could we say that if it's constant temperature, then it's insulated because the partial derivative is 0? No, you can't say that. So the partial derivative being 0 and the function being 0 are two different things. And I think if you let, the good way to get all this stuff straight is let's go back to my top hat question from earlier. Yeah, this one, the animation. Hopefully it will load. So I think this is a good place to see what's going on. So first of all, let's hit play and see what happens. So the left end of the bar, let me open this up. The left end of the bar is this temperature 0 thing. So the left end is always at 0. And the right end is the insulated thing. So the right end always is flat. So that's what's going on in this picture. The left end is always at 0. The right end is always flat. So the right end is insulated and the left end is held at temperature 0. And you can see that it's always 0, but the slope is not 0. And this one, the slope is 0, but the function is changing. So the value can go up and down, and the slope here can change on the left-hand side. But so don't get the two types of derivatives mixed up. So this is what's happening. We have one thing being 0. We have the derivative is not 0, and vice versa. So that's a good question. Let me go back to your questions. If boundary values and boundary conditions are not the same thing, how come in the quiz they are called boundary values? So all boundary values are a type of boundary condition. It's like, yeah, I have the paper up. Okay, so it's like this, right? Boundary condition. So boundary condition is like the big bubble. It includes boundary values. Boundary conditions include boundary values, but if somebody says what is going on the boundary, it might not be a value. It might be a condition. So for example, partial xu of t0 equals 0. This is a condition, not a value. So it's a condition on the derivative, not the value of the function. That's why it's not a value. So on the quiz, I guess it was a boundary value. Okay. I think that's good questions. If the boundary conditions are not defined, can we still know what happens in the center of the graph? No. So if somebody gives you the PDE and does not give you the boundary conditions, then they have not given you a question that can be solved. So just like, it's almost like not specifying the problem correctly. So to specify a PDE problem correctly, you need the equation, which is what's happening with the partial derivatives, and you need the boundary values. If you're missing the boundary values, you don't have a problem. It's just not specified. Nobody can figure out what's going on. So you really do need the boundary values to come with or the boundary conditions rather, to come with the PDE, or they haven't given you a problem. Okay. If the right end this is a great question. If the right end is insulated, why does the temperature still go up in the simulation? Let's go look at the graph one more time. And I think you can answer this question if you know about how heat flows. So in this graph, let's hit play. Maybe somebody can write it in the chat. So the right end is insulated. There is no heat flowing out of the right end of this bar of steel. So how is the temperature going up at the right end? What could possibly make the temperature go up on the right here? So if you know the answer, feel free to do it in the chat. But it has something to do with how heat works. Yeah, I'll say it in a second if nobody wants to take a stab at it in the chat. So someone said heat energy can go in but can't leave. That's not what's happening. So one possibility would be that the heat can go one way or the other way, but that's not what's happening. Heat, when it's insulated, it can't go either way. Someone said because heat from the left end is flowing to the right end. That is exactly what's going on. So at time t equals 0, this bar started out really hot on the left side and really cold on the right side. So even though the right side is insulated and no heat can go in or out of the bar on the right, it's an insulated bar, heat can still come in from the left side of the bar. And that's exactly what's going on. So when I start time, at time 0, it's hot over here and cold over here. And even though no heat can go in or out over here on the right, when I start moving things, the temperature on the left goes down and the temperature on the right goes up. And that's because heat is flowing from the left to the right side of the bar. So I think a few people said that. Heat transfer, so it's heat transfer from the left end to the right end. The insulated just means that there's no heat transfer from the right end of the bar out of the bar, if that makes sense. And so I believe this simulation, I'll tell you guys how this simulation came to be. Last year when we did this course, it was when Game of Thrones was really popular. And this graph, what it represents, I'll draw a cartoon of it right here. So this graph represents, you have Jon Snow, and he has a sword, and the sword is stabbed. This is his sword, and the sword gets stabbed into an ice zombie, into a White Walker, and the White Walker is cold, so he is cold, and the left and the other end of the sword is insulated. So the left end of the sword is always temperature 0 because it's stabbed into the icy zombie, and the right end of the sword is insulated. No heat can go in or out of the right end of the sword. That's how we came up with this problem. Yeah. Okay. Can I explain again why the temperature at the left end drops to 0? In this graph, the reason the temperature is 0 is that was just the specified boundary condition. So in the top hat simulation, the boundary conditions are u of t comma 0 equals 0. This is on the left. And partial x of u of t comma l equals 0. This is on the right. So write that. You can see that here. So that's what's going on in the simulation. On the left end, it's temperature 0. And on the right end, it's insulated. And that doesn't mean that the temperature at the right can't go up. It can. The temperature can go up on the right. It's just that no heat is flowing from the sword to outside. Okay. Can I explain again why partial being 0, it means insulated? So the explanation I gave was that when there is no temperature gradient, this represents the temperature gradient. When there's no temperature gradient, there's no heat flow because heat moves only through having a difference in temperatures. So when there's no difference in temperatures, there's no temperature gradient, then there is no heat flow, and that's the same as insulated. Okay. Yeah, and you know, there's a really good explanation of this kind of thing going on in the 3 blue 1 brown video of where this whole thing comes from and like figuring out how temperature flows around. So I think I really recommend you watch that and see the explanation there. It's better than I can do. Okay, I think I've answered all the questions. Okay, really good questions, guys. That was really good. We are going to start doing some nitty-gritty, finding the solutions. I'm going to start with some light things before we get too heavy with the math. Okay, so I'm going to move on from this discussion from boundary conditions. So you should, I think if you're still confused, you can read the textbook that has a few page explanation of what's going on. There's also the 3 blue 1 brown video. And then I'm also going to have office hours, I think, tomorrow. So we can talk then, or I could like put something else out about it. But yeah, I know they're confusing at first. There's the two you got to know are this insulated, which is the derivative, and the temperature being 0. Okay, so we're going to move on to how do we solve these things. And we're going to start by just like coming up with a strategy before we actually solve it. And so the first question says, what solution method should we use to try and find solutions? So again, this is one of those fun questions where there's no wrong answer. You can put in anything you want. What method of solution would you use? That's the question. Okay, so this question in the chat, someone is saying, if there is heat flow from one side of the bar to the other, why do we say that there is no flow? So when we say there's no flow, we mean, and when I say no heat flow, when I wrote no heat flow, maybe I should say no heat flow at x equals 0. This is all at x equals 0. So what this is saying, this condition means there's no temperature gradient right at the end of the bar, which means there's no heat flow right at the end of the bar, which means that that end is insulated. So it's sort of like, you can imagine it's like, here's x equals 0, and there's sort of like a wall right at x equals 0. And it's keeping heat from going from one side of the wall to the other side of the wall. So heat cannot cross x equals 0. Heat can still come in from I don't know, wherever, and get to x equals 0. So the temperature at x equals 0 can go up and down from one side, but there's nothing else can hit it from the other side. So there's no flow across x equals 0, even though you can have flow from the right to the left side of the bar. That's maybe, I don't know if that answers the question in the chat. Someone said, don't we need two boundary conditions, slope and temperature for each end? No, so it turns out you only need one. You specify one of them, and the other one gets like solved for. So you could figure out what the other one is, the slope or the temperature, but one of them is specified, and the other one is free. Yeah. Okay. What solution method is the question? Maybe I'll do a 1-minute timer here. Okay, there's like 30 seconds left. I think most people have answered. There's like 5 people left, so maybe those 5 people can put something in. Okay, time is basically up. Let's see what people said. What's the best solution method in the course? That could be the other question. People are saying Fourier series. Some people are saying Laplacian, but the most common answer is ansatz. Ansatz question mark, also good. Ansatz. So Fourier series is not the right answer. So there will be some Fourier series, but the Fourier series, it turns out, are not part of finding the solution. So if I go back to the picture I had here, finding the general solution does not involve Fourier series. It turns out that Fourier series are only going to be involved in this initial condition thing. So if someone gives you an equation and boundary conditions, to find the general solution, there's no Fourier series. And then when we do this last little bit, that's where the Fourier series are going to come in. So it's not Fourier series. What else did people say? Get rid of the word cloud. Some people said separation of variables. And I think the correct answer is an ansatz method, and it's a separation of variables ansatz. So what we are going to do to solve this equation, it's going to be an ansatz method. We are going to try, as soon as you're trying, it's an ansatz method, try a solution of the form u of tx is some function of t times some function of x. So this is what they do in the textbook, and in the video, they try a solution that is a function of t and a function of x, and is multiplied together. So not all functions in the universe look like this, function of t times a function of x, but we're going to try specifically a solution like that. So this is an ansatz method, ansatz, and if you want, it is a separation of variables So we're saying, let's try this and see if we can make it work. And so that's what we're going to do after the break. I think we'll take a 10-minute break here. We're going to try the separation of variables ansatz. We're going to see what has to be true about the functions t and the function x, and we're going to get a solution that way. And this should totally remind you, by the way, in chapter 3, or chapters 3 and 4, we tried a solution of the form f of x, or f of t times v. We tried a solution like this. So this was for x prime equals ax. We tried a function of time times a fixed vector. And the fixed vector is sort of like a function of space. So it's really the same exact ansatz we did in chapter 3 or chapter 4 a long time ago. If you remember that class where we tried something like this, we figured out what had to happen. We're doing the same exact thing again. So nothing really like completely new here. We're just combining old ideas in the course in this new funny PDE space. Okay, I think we're going to take a 10-minute break here. If you have questions, especially about boundary conditions, it's a good time to ask them in the chat. So I'll be around, but we're going to start up again at 10:10, I think. So yeah, go, I don't know, go have a glass of water. I watched Chicken Little last night. And you changed your like picture to Chicken Little. Oh wait, no, that is a person. That's not a chicken. I apologize. Okay, maybe I should turn my sound off so I stop saying dumb things. Will top hat marking be changed anyway, or is it the same as before? Yeah, it's the same as before. So participation only, rounding up. Someone wrote, why is the slope at the left of your graph 0, but not on Desmos? Oh, you mean over here? So, yeah, okay, here. So this is the Desmos problem. This was the Desmos. So in the Desmos problem, the temperature is fixed on the left, and then we have insulated end on the right. And when I was talking about it here, this is insulated on the left. So this is at x equals 0, whereas at Desmos this was at x equals L. Maybe that's the confusion. So you have to specify what happens at either end, and there's two options at either end. I'm not sure if that answers Andy Wang's question. Oh, okay. Someone says for the Desmos simulation, why is the... Let's go back to the Desmos simulation. So there's the Desmos simulation. Why is the graph flat on the right side when we didn't specify that the right side was insulated? So when I solved this equation and made the thing, it was specified that the right side was insulated. In the question that I gave you, the whole point of the question was I didn't specify what happened in the question, so there was not enough information to say what's going on. So to get what was happening in the Desmos graph, you really need the thing that I have moved now, which is this. So to properly find the Desmos graph, someone would have told you u of t0 equals 0. That's the left boundary condition. They would have said the partial derivative x is at x equals L is 0. That's the right boundary condition. And they would have said u of 0 comma x is 10 minus 5x at t equals 0. That's the initial condition. So the Desmos thing is the solution to this 3-ingredient thing, the initial condition and these two specific left and right boundaries. Are we solving the heat equation for 2D or 3D? We're doing the 1D heat equation. So we're doing a long, thin bar, so it's one-dimensional. The dimension is the number of space directions you have. So we only have x going between 0 and L. It's the 1D heat equation. We'll do something related to the 2D heat equation next week. Yeah, vaguely. But it gets harder. So, 1D is already plenty hard. Where is the baby? The baby is sleeping right now. Or maybe he's awake. I don't know. We'll see. Maybe we'll get the baby at the end if he's requested. I hope you're doing well. Yeah, it's been okay. How have you guys been holding up? Has it been? I have no idea how your life is going right now. Do you have a lot of work, or has it been easier? Oh, so the link to download chapter 1011 is in the syllabus. So in the syllabus it says like, go to the Wiley publisher website at this link and download chapter 1011. So the link is there. Hopefully it still works. Eric wrote, life is hard. But I'm asking, is it harder than before? That's the question. We know it's hard. That goes without saying. The painting is a secret. I'm not going to tell you what happened to the painting. This is the top secret stuff. I didn't know there was eyeball emojis as well. This is news. Okay, so apparently somebody put the free chapters together in some kind of PDF. Yeah, so chapter 11.1 especially is decent. Like, I think it's worth looking at. So take a look at that one. I think it's better than most. Chapter 10 is not great. Chapter 10 is written for like some kind of really pure math person, but chapter 11 is okay. So you can see what that's like. Okay, it is 10:10, so I'm going to get started here. If you have any last-minute questions, now is the chance to ask them. So we're going to start with this thing. We're going to try this ansatz solution, this separation of variable ansatz solution. We're going to plug it in and see what happens. That's what we're going to do. Okay, so here we go. This is like the trick. Like, how do we solve equations in this class, right? We have a clever ansatz. We just use it and plug it in, and we just like hope that it works. So that's what we're going to do. We're going to try something like this. U of tx is t of t times x of x. So this is what the textbook calls them, t and x. But I am going to change notation here. I'm going to call it f and g. Which one's f? Which one's g? I'm going to call this g of t times f of x. And the only reason is so that when I say x, you know I'm talking about the variable, not the function. So that's why I'm calling it f and g. F and g are the functions, x and t are the variables. That way there's no getting mixed up. Okay, so we're going to try this. U of tx is g of t times f of x. if that's true, then let's compute the partial derivatives. Partial utx equals, so take the t partial derivative, that you just get a g prime of t times f of x. No problem. And if you take two x derivatives, you get g of t times f double prime of x. So taking the partial derivatives is not bad. Now we're going to take ut equals alpha squared uxx. That's the PDE. And we are going to plug this stuff in. So the problem I'm going to solve is ut equals alpha squared uxx with boundary conditions u of t comma 0 equals 0, u of t comma l equals 0. And this is example 1 in the textbook, if you want to follow along in the textbook. Example 1. Okay, that's the PDE I'm going to solve. I'm going to plug this stuff in. So plug in. So if you plug that in, you get g prime of t times f of x. That's the ut, is this thing. And on the other side, you get alpha squared. Uxx is g of t times f double prime of x. That's what we're trying to solve for. And it looks scary now, but there's a little trick you can do, which is you put all the things with t on one side, all the things with x on the other side. So you get g prime of t over g equals f double prime over f. I just want to make sure I'm matching it up with how they do it in the textbook. And they put the 1 over alpha squared with the g's over here. So I just rearranged this equation to put all the stuff that depends on t on the left and all the stuff that depends on x on the right. And here is maybe the one important idea. This guy depends only on t. This guy depends only on x. But x and t can change. So if x and t are changing, and this thing depends only on t, and x and t are changing, and this thing depends only on x, then actually the thing that must be true is both must be a constant. And the reason is, if they weren't a constant, then you could fix t, leave t fixed, and then as x would change, the right-hand side would change, but the left-hand side wouldn't change. So if they were not a constant, then because you can change one variable without changing the other, something's going to change here, and that's not good. So both of them have to be a constant because of this t and x thing. This is 11-4, so it's chapter 11. I'm doing equation 7. I'm about to do equation 8 in chapter 11.1. So I guess the page numbers are weird. They're numbered 11 dash things. Yeah, that's right. So I'm on page 11-4 in chapter 11. Hopefully that helps. Okay, so both of these are constant. So we're going to, they're equal to some constant. So you got to give that constant a name. And this seems really weird. We're going to give the constant the name minus lambda. It's minus lambda. I don't know why people decided to call this minus lambda, but that is what they decided. So that's what we're going to go with, just to match the textbook. So this is the big leap. This must be a constant. The constant is called minus lambda. And now we're going to solve for the functions f and g individually. So far, what have we done? We had this idea, try this separation ansatz. We plugged the separation ansatz into the equation, and we have two equations, one for g and one for f. So we have a g equation and an f equation. The g equation says g prime over g, 1 over alpha squared, equals minus lambda. Or another way to say that is g prime of t is minus lambda alpha squared g of t. So this has an easy solution. This is the world's most famous first order equation. The solution is g of t is some constant c times e to the minus lambda alpha squared t. So hopefully you've seen this before. In fact, you definitely have seen this before. We've done this in class a bunch of times. This is the world's most famous first order equation. It's an exponential. There's an arbitrary constant in the front, and we have this exponential decay. I want to point out two things. So one is the alpha squared. Alpha squared is from the problem. So alpha squared was given in the PDE. It's this alpha squared. So this is given in the PDE. And alpha squared in the context of the heat equation is just like how thermally conductive the thing is. So even the textbook even has a table that's like copper, alpha squared is 7, like steel, alpha squared is 8, or whatever it is. So this is some number that depends on the physical properties of the system. It's some physical thing. That's alpha squared. What the hell is lambda? Lambda is a slippery thing. So alpha squared, I'm pointing out, is a real life thing, but lambda is some made up slippery thing. Lambda is the lambda from here. So lambda is not a real life thing yet. Lambda is some constant that we made to make this equation work. So we'll see what lambda is in a sec, but for now it's not as real as alpha squared. Alpha squared is some honest real life parameter. Lambda is this funny thing. Okay, that was the G equation. Now I'm going to solve the F equation. The F equation, what was the F equation? The F equation says F double prime of x over f of x is minus lambda. And this is a second order equation. F double prime of x plus lambda f of x equals 0. And this has solutions. There's more than one possibility for what the solutions could be. It depends if lambda is positive or negative. So if lambda is positive, then you get sines and cosines. So you get f of x is c1 sine of square root lambda x plus c2 cosine of square root lambda x. That's if lambda is positive. If lambda is negative or 0, you get something else. If lambda is negative, you get exponentials. Okay, so those are the three possibilities. If lambda is positive, you get sines and cosines. If lambda is negative, you get exponentials. And if lambda is 0, you get, it's like the multiply by t rule, it's a multiply by x rule, you get c1 plus c2x. Okay, that is the F equation. That's the general solution for the F equation. And now what we are going to do, so what have we done so far? We have the G equation, we have the F equation. We've solved both of them. Now what we are going to do is use the boundary conditions, which I made a big deal about earlier. The boundary conditions are going to be used to find lambda. That is the surprising thing, is that the boundary conditions will be used to narrow down what possibly could be lambda. And that is why you need the boundary conditions. Without the boundary conditions, there's no way to find lambda, and like this whole thing will fall apart. Okay, before I do that, I want to address the question in the chat. Someone said, why were both ratios equal to a constant? So this is the one important trick in separation of variables. The reason they are both equal to a constant is because in this equation, the left-hand side is a function of time. Left-hand side depends only on t. And the right-hand side depends only on x. And so if one of them wasn't a constant, like let's pretend the right-hand side was not a constant, that means it's changing as x changes. So as you change the x value, this is not a constant, and so it's changing. But if you change the x value and leave the t value fixed, the left-hand side doesn't change. So what that means is the right-hand side, you told me it wasn't a constant, it was changing, but the left-hand side is a constant. So that is why, because of this thing, one side depends only on t, one side depends only on x. That means that these two things both have to be constants, or else you get a contradiction. You can change one without changing the other. So that is why they both have to be constant. That is the one important trick in separation of variables, is this one thing of time, one thing of space. This might remind you a little bit of the eigenvalue thing we did. So if you remember that class we found the eigenfunction or the eigenvector eigenvalue solution. It was the same kind of thing. It was about pointing in the right direction. Anyway, that is the important trick. So the reason they must be a constant is one side depends on t, one side depends on x. Okay. So here we are. We plugged this stuff in. We solved the g equation. We solved the f equation. Now I'm going to use the boundary conditions to solve for lambda. So what was the boundary condition? The boundary condition was u of t comma 0 equals 0 and u of t comma l equals 0. Those were the given boundary conditions. In a different problem, you have different boundary conditions. You're going to find different lambdas. So that is changes from problem to problem. In this problem, this is the boundary conditions we're doing. What does this mean in terms of f's and g's? This means g of t times f of 0 equals 0, because u is, we said, is g times f. G of t times f of l equals 0. Okay, so g times f of 0 equals 0, and g of t times f of l equals 0. But g was just an exponential, so g has to be non-zero. If g was equal to 0, then everything is 0. We just get like a boring solution. So we definitely want g to be non-zero. And if g is non-zero, it means we can cancel it out. So we have, from the boundary condition, f of 0 equals 0 and f of l equals 0. And I want to remind you guys what we have on the page here. We got f of 0 equals 0, f of l equals 0, and we have this thing, f double prime plus lambda f equals 0. All of these things together are chapter 10.3 eigenfunction problem. And that is why what we're doing right now is exactly why chapter 10.3 exists, is to solve problems like this. And when you have this kind of thing, there's only some values of lambda that work. This was the very last top hat question we did on Monday. And by looking at the types of solutions you can get, you can narrow down what lambda has to be. And that's what we're going to do right now. Do we always set the equations equal to negative lambda? Is that the same process for every equation? So again, over here, negative lambda, you could have called it c or something. Like you don't need to, it's just, the point is it's just any constant. And so you can give it your favorite letter. I don't know, if your favorite letter is A, good time to use the letter A. The textbook calls it negative lambda, that's why we're calling it negative lambda. Why negative is kind of mysterious, for sure. Lambda, in some sense, this is an eigenfunction problem, so I guess they want to use lambda for eigenvalue. Why did we cancel out g of t again? G of t is non-zero. G of t is non-zero. So the point was, because g is non-zero, if g times something equals 0, then the something has to be 0. Okay, so we have this eigenfunction problem, and we got to solve it. That's what we're going to do. Do we always set the equations equal to a constant to solve them? Yes. So when you do separation of variables, you split it up like this, and they're equal to some constant. That is how the separation of variables on Zotz works. Okay. So this is the problem we have. F double prime of x plus lambda f of x equals 0. F of 0 equals 0. F of L equals 0. And I actually even already solved for the possibilities for the f's. So there were, if lambda was positive, you get sines and cosines. If lambda is negative, you get exponentials. And if lambda is 0, you get a linear function. And I want to point out that we've sort of done this already. So if f of 0 equals 0 and f of l equals 0, let's do it this way. I'm going to say there's three cases. There's lambda positive, lambda negative, and lambda equals 0. Let's write them all down. Let's just do it. So c1 cosine square root lambda x plus c2 sine of square root lambda x. If lambda is negative, you get exponentials. E to the square root lambda x plus c2 e to the minus square root lambda x. C1 plus C2x. So those are the three possibilities. And then we have this boundary value problem with f of 0 equals 0 and f of l equals 0. And if you plug in f of 0 equals 0 and f of l equals 0 into these two possibilities, the negative and 0 case, so plug in these are the boundary values. you plug those in the negative and 0 case, you're going to get that C1 equals 0 and C2 equals 0, and C1 equals 0, C2 equals 0 in the 0 case. So when lambda is negative or 0, and you plug in, no matter what happens, it's just boring. You just get the 0 solution. So this is the 0 solution. And what that means is there is no non-zero solution when lambda is negative or 0. So because of this, there is no non-zero solution when lambda equals 0 or lambda is negative. Okay, so far what we've done is we have ruled out all the possibilities for lambda except for lambda positive. And that is because we're looking for solutions. Of course, the 0 solution is not a good enough solution for us. We found the 0 solution, but that's boring. We're looking for a non-zero solution. And because of this math, when you plug this in, the only solution when lambda is negative or 0 is the 0 solution, so that's no good. And that means that lambda must be a positive number for us to get to have a chance of finding a non-zero solution. So we're on to this last little bit here, which is lambda being positive. And we're looking for a non-zero solution. So the question is, for what values of lambda does, let's call it, I don't know, these two things, does it have non-zero solutions? That's really what we're doing. And so if you plug the stuff in, you get two equations with two unknowns, f of 0 equals 0 and f of l equals 0. You get, so I'm plugging in into this guy. You get at f of 0 equals 0. So if you plug in 0, the sine of 0 is 0, the cosine of 0 is 1, you get C1 equals 0. That's from f of 0 equals 0. So I'm plugging in here. And if you plug in f of l equals 0, you get, okay, I'm going to plug in f of l equals 0 and C1 equals 0. So because C1 equals 0, there is no cosine term. So you just get C2 times the sine of square root of lambda times L equals 0. That's what we got. I plugged in x equals L into this equation. I plugged in C1 equals 0, so there's no other term. And now we're looking for non-zero solutions. So for what values is there a non-zero solution? The sine of something has to be 0. So the something has to be a multiple of pi. That's the rule. So for this to be for C2 to not be 0, it must be, if C2 is not equal to 0, then the square root of lambda times L must be a multiple of pi. How should we write down a multiple of pi? I'm going to write it down as n times pi. And that is how you find what the lambdas have to be. So this equation here, coming from this funny sine business, is going to dictate what the values of lambda have to be. And they have to be such that the square root of lambda times L is a multiple of pi. So if you just rearrange this one more step, you get, so to have non-zero solutions, square root of lambda times L equals n times pi, which means that lambda is n pi over L squared. Okay, and n is any integer. Okay, so those are the possible values for lambda. Let's summarize what we have already. So summarize. So we had G was up here. G of t is C times e to the minus lambda alpha squared t. Lambda is this thing. G was that, and f of x rather. Well, f of x, we're going to take our information from here. F of x is the C2 times the sine thing. There is no cosine because C1 was 0. So f of x was equal to C2 times the sine. It's the sine of square root of lambda times L, but we know what that is. That's n pi x over L. So I just took the formula for f and I plugged in what lambda is. And lambda is equal to n pi over L squared. So these are the three ingredients, and the solution is the product. U of tx is the product. If you multiply it all out, you get, let's just write f times g. C e to the minus lambda alpha squared t times the sine of n pi x over L. Let's write it like that. There's two constants here, c and c2, but they're arbitrary constants, so if you multiply them together, you can still call that an arbitrary constant. So I think maybe let's drop the arbitrary constant on one of these. I'm going to drop the c2 just so we have a c, and that's just because they're getting multiplied together. So you don't need two constants, it's just one constant. So that is the solution from separation of variables. Solution comes from separation of variables. And I would say these two ingredients, what is the value of f and what is the value of lambda, these come from solving a boundary value problem. And we solved the boundary value problem, we got f and lambda, and then we put that together with the solution. The function g, that one was easy. That just came from the equation. Okay, that is sort of the hard work of solving the PDE. It's a good time to stop me for questions here. So we found a solution using the ansatz method. I'm going to open up a top hat question here in a second. Someone in the chat said we're always looking for a non-zero solution. That's right. So the zero solution is boring. But the non-zero solutions, those are interesting. Okay, so what we've done with separation of variables, we found this very special solution. This solution was separable. It has a t part and an x part, and they're multiplied together. In top hat right now I have open, and I said, so far we found some special solutions, these ones. Why did I say some? Because n can be any integer. So actually we found a whole family of solutions. For any value of n, we have such a solution. So we have a whole family of these solutions, but the question is, in top hat, we found some special solutions using our ansatz. How can we find the general solution? Okay. Is there a case where there is no solution? I mean, there can be, but not in this problem. So this problem has solutions. It's possible I could ask you a question, like there could be a PDE with no solutions, but in this one, there are solutions. Is lambda always equal to n pi over L squared, or is that only for this question? That's only for this question. So that's a good question as well. This came, and it came from the boundary conditions. So, as long as you always have the same boundary conditions, you'll have that. Someone else asked, why is the C2 and F crossed out? The reason I crossed out the C2 is because the only thing that matters is the function U, which is F times G. So I could have written C times C2, but C and C2 are just arbitrary constants. So there's no point in multiplying them together, because when you multiply two arbitrary constants together, that's just a new arbitrary constant. So instead of calling this one C and calling this one C2, I just got rid of this one, and I just have one arbitrary constant. Okay. Those are the questions in the chat, which are good questions, by the way. Okay, some people are still thinking about this. I think it's a hard question in top hat. We found some special solutions. How can we find the general solution? I'm going to add a timer here for a minute, but it's something we've done before. We've done exactly this before. And in fact, if you remember back to the class from chapter 3 where we did this, we tried a solution of the form function of time times a vector v, and we found what the function of time had to be, we found what the vector v had to be, but that wasn't the general solution. So we had to do something else. And we're going to do the same thing here. So I'll give you another 30 seconds. Good time to ask questions as well. And again, all of this is, if you're having trouble following what I'm doing, it might help you to follow along in the notes as well. So especially after class, if you want, you can like rewatch the video and follow what I'm doing or what I'm saying. And you can also read the chapter 11 notes from the textbook. And so they have the same kind of derivation there, in a little bit less detail than what I do. So they skip some steps. Okay, I'm really curious what you guys wrote. We found some special solutions to the heat equation using our ansatz. How can we find the general solution? Some people are saying superposition. Some people are saying initial conditions. Boundary. So boundary conditions we've already used. We already used the boundary conditions when we came up with the boundary value problem for f. So boundary conditions, we've used those up. People are correctly seeing we haven't used the initial condition yet. So actually the problem that I want to solve, and I'm going to solve in a minute, I haven't told you the initial condition yet, but the initial condition that we want to solve for will be some function. So for example, someone will say u at time t equals 0 at x is equal to 20. This is the problem that is in the textbook. So this will be the initial condition. And if you remember how like things have been going in this course so far, we find the general solution. And in this case, there's one constant c. And then we find the initial, once we find the general solution, we find the value of c that makes the initial condition work. So so if I was going to solve, like you guys are saying, for initial condition, I have this solution with a c, and so the question would be, what value of c makes it so that c times e to the minus lambda alpha squared t sine of n pi x over L, where here lambda is equal to n pi over L squared, so that this is equal to 20 at t equals 0. So when you plug in t equals 0, the exponential goes away. When you plug in t equals 0, you just get c times the sine of n pi x over L. So really, like, what value of c and what value of n makes it so that c times the sine of n pi x over L is equal to 20? That would be what we're trying to do. What value of c works at time t equals 0? And the answer is there is no value of c. There is no value of c, and there's no value of n that makes this equation work. So there is no value of c that works. So why am I saying this? The reason is, so people who said initial conditions or initial values in Top Hat, using the initial conditions won't let us find the solution. So the initial conditions on their own are not enough to find the solution. So yeah, lots of people are saying initial values. Some people are saying Fourier series. So where is the Fourier series? So Fourier series is something about an infinite sum. Where is that here? That's what you should be asking yourself. Okay. So some people are on the right track. Some people are on the right track. I'm going to open it up one more time and let you guys think for another minute or so. How could we take this solution? So sort of what I've been telling you so far is we don't have the general solution yet. So if we had the general solution, we could make it work for this initial data, but we don't have it yet. And we need something more general before we can use the initial value. So using the initial values, we don't use them yet because we need to make it more general first. So I think you guys are on the right track. Another 30 seconds or so in Top Hat. And then I will reveal what we should do. Okay, so this was a little aside. Okay, I'm going to go back to Top Hat now. People are jumping on board the superposition train. It went from 8% to 16%. Maybe there's other people who said it as well. Superposition is the right answer. So The superposition principle says if you have some solutions, if you have a solution and you have a different solution and you add them together, you still have a solution. And we have a lot of solutions here. For every value of n, we have a solution. So you tell me what n is. Maybe you say n is 3. Then I know what lambda is, and I have this funny solution. And by combining different values of n together, then we can get a more general solution. So the answer is, to how do you find the general solution, is to use the superposition principle. And we're going to add together some of our solutions. So as an example, if n equals 1, then lambda is equal to pi over L squared. So you get the solution c times e to the minus pi over L squared alpha squared t times the sine of pi x over L. That's one solution. Here is a different solution. When n equals 2, we have a different solution. We got lambda is 2 pi over L squared. And the solution is c times e to the minus 2 pi over L squared alpha squared t times the sine of 2 pi x over L. So far what we've done is we have found these two solutions. We found this one, we found that one, we also found a whole bunch of other ones. But the point is, this is a solution, this is a solution. If you add them together, that's still a solution. So now we're going to add them together. And if you add them together, it's still a perfectly valid solution. That's what the superposition principle says. And this works because the equation ut equals alpha squared uxx is linear. So because it's a linear equation, that means that the superposition principle works. So if you add these together, okay, now you got a problem because these things are both called C. So if you add them together, you got to make sure you know that this C is different than that C. So I'm going to call this one C1. I'm going to call this one C2, just to keep them separate. And that means that if you add them together, C1 e to the minus pi over L squared alpha squared t times the sine of pi x over L plus C2 e to the minus 2 pi over L squared alpha squared t sine of 2 pi x over L is also a solution. Okay, so far I added these two things together. I got this solution. Liam had an excellent question in the chat. How do we know that the two solutions span the entire solution space? In fact, these two solutions do not span the entire solution space. So adding these two together, this is still a solution. It's also a solution, but we still don't have the general solution. So there's a C1 here and a C2 here, but in fact, I think you can probably, if you use your head and think of the pattern, you can think of something else that will also be a solution. And we found a whole bunch of solutions over here. This was only 2 of them. What about the other ones? So in fact, you can do this with n equals 3. So that's what I'm going to do now. When n equals 3, lambda is 3 pi over L squared. That's also a solution. You should chuck that in as well. So if you throw that in, you get a plus C3 times, okay, let's write this one down. E to the 3 pi over L squared alpha squared t times the sine of 3 pi x over L. And if you're, if you're following along, you should know that, okay, that was 3, but what about 4? What about 5? So in fact, no matter how many of these you add up, you will not span the entire solution space. You need to add up infinitely many. So you do the superposition principle. The most general way to do it is to add up infinitely many things. And that is what we're going to do. If you follow the pattern, and you add up infinitely many, how should you write down infinitely many things? You're going to have to use an infinite sum. So it's going to be the sum. N is going to go from 1 to infinity. And it's going to be Cn e to the minus n pi over L squared, that was lambda, alpha squared t, times the sine of n pi x over L. And what this is a superposition of all the infinitely many solutions we found. For every integer n, we added them, we got a solution. Here I've added all of them up. That's the most general superposition we can do of the solutions we have. You still might wonder, does this span all possible solutions? And the answer is yes, this spans all the solution space. And the reason is because of Fourier series. So this is the most general thing we can possibly come up with. And because we know how to do Fourier series, we know that by choosing the right constant Cn, we can get to any function we want. And so that is this is the general solution, which we found by doing superposition on our special separation of variables solutions. And because of Fourier series, we know that this will encompass all possible solutions. So that is the long and the short of finding the general solution. This is the general. Okay. Someone in the chat wrote, why do we have to add up infinitely many things to obtain the general solution? The reason is, if you only added up finitely many things, there would always be something on this list that you are missing. So for sure, adding up finitely many is not enough, because when you add up finitely many, you are missing the next thing on the list we found. So finitely many is definitely not enough. It's not even like obvious why this infinitely many is enough. The only reason is because Fourier did some good work to figure that out. Does this have anything to do with the world's most important orthogonal set? Yes, it does. So these signs are part of the world's most important orthogonal set, and the fact that the world's most important orthogonal set is a basis is exactly why this spans everything. So that's the general solution. We found it with the superposition principle. Now I'm going to show you guys how to find the constant Cn, but this is something we already did in chapter 10.2. So that's the next thing. Yeah, okay, let's do that. So I'm going to solve for the initial condition u at t equals 0, x equals 20. So this is the textbook example. This is at t equals 0. And so what I would like to do, solving, what does solving mean? Well, after you found the general solution and someone says solve for this initial condition, they're really saying find the c's. Find the constants C1, C2, right? So once we have the general solution, solving means finding the constants. So that's what I'm going to do. I'm going to plug in. So I'm going to plug in t equals 0 into my general solution. So the general solution, when you plug in t equals 0, it says n equals 1 to infinity of Cn times the sine of n pi x over L. So this exponential term, I plugged in t equals 0, that was 1. Maybe I'll write it 1. And that's equal to 20. So this is the function. This is the function, the constant function, which is always 20. Okay, so how do you find the constants C1 to Cn? This is a Fourier sine series for 20. And so what I'm going to do is I'm going to do the inner product. So this is, now it's a chapter 10.2 problem. I'm going to do the inner product Okay, yeah, so I'm about to do this. Somebody in the chat wrote, is there a reason why you said Fourier series was incorrect earlier? So I would say to get to this, we're using Fourier series now, that's for sure. But earlier, when we came up with the solution, we didn't use Fourier series. So Fourier series comes into play of, after we've done the superposition principle, the idea of Fourier series is the idea of how do we solve for these constants Cn? Why should there be constants Cn in the first place? So I would say we did the separation of variables ansatz. That didn't involve Fourier series. We did superposition principle to add them together. That didn't involve Fourier series. Like, you know, we did that in chapters 3 and 4 and stuff. And now, finally, when we're really doing the nitty-gritty solving the initial condition, that is, at the last second, is where the Fourier series comes into play. And so this is exactly where we're using the world's most important orthogonal basis and that stuff. So to get to this position, to get to this solution that we found over here, there was no Fourier series. It was just superposition principle and ansatz. But now we're using Fourier. Maybe that clears that up. Okay. So this is a chapter 10.2 problem. I'm getting a little bit low on time here, so I'm not going to do the details. I'm just going to tell you what the answer is. So hopefully you know how to do this kind of thing. You do the inner product of the sides, and I believe what you get is, yeah, here you go. You should get that Cn is equal to 80 over n times pi if n is odd, and 0 if n is even. So the initial condition, you take the general solution, you plug in t equals 0, then you have a Fourier series problem, and by doing the world's most important orthogonal basis, chapter 10.2 stuff, you solve for the Cn's. And once you have the Cn's, you plug them back in, and now you have the solution. So what happened to the exponential term in the sum? I plugged in t equals 0. So when you plug in t equals 0, the exponential, it depends only on t, and so that became a 1. Yeah, okay. So the solution to, let's remind us what the problem was. The problem was partial t u equals alpha squared partial x x u with boundary conditions. U of t 0 equals 0, u of t L equals 0. What is the length? Yeah, that's a good question. I might have done a goof here with the length. Yeah, I think this formula, this 80, it only works for the textbook example where they took L equals 50. So probably this should be yeah, okay, so let's put L equals 50. This is the textbook example that we're doing. You can probably find this just in terms of L, but you know, I just didn't have time for that right now. Okay, so this was the boundary. These were the boundary conditions, the BCs. This was the PDE. That's the PDE. And we had the initial condition. The initial condition was u at 0, x equals 20. That we were doing L equals 50. What is the solution to that? It is the sum. Okay, it's one of these sums where you only sum up the odd terms. So there's more than one way to write it, but why don't we write it like this? N equals 1, 3, 5, dot, dot, dot. And then you do 80 over n pi times e to the minus n pi over L squared alpha squared t. I think we did alpha equals 1. No, they just left it as alpha. Okay, that's fine. Alpha squared t times the sine of n pi x over L. So there you go. That was the solution to the problem. Okay, so there were 3 ingredients to specifying the problem. There's the PDE, the boundary conditions, and the initial condition. The PDE and the boundary conditions, that is how we found the general form of the solution up here. And then using the initial condition and Fourier series, we found the constant Cn. And that's how we got the solution. L is the length of the bar. In this problem, it's 50. Why is it only odd terms again? It's because when you calculate the Cn's, there's 0 when n is even. So that is example 1 in the textbook. I skipped the details of how you get the coefficients, but that is a chapter 10.2 problem. It just involves doing some integrals. So it has to do with the integral of the sine function. I have this in top hat. I have this thing displayed. Let me go one more. So I have a Desmos graph of what is going to happen So I have an animation of this function, this crazy function here. I have an animation of it in Desmos, and I'm going to show it to you. But before I show it to you, I want you to predict what's going to happen. So, yeah. Okay, so this is the same problem. In this one, L was 2, but that doesn't matter. And the initial condition was 10 instead of 20, but that also doesn't matter. And the question in Top Hat is, what does the solution look like as t goes to infinity? So you can look at the algebra, or you can just guess based on what you like, your understanding of how the thing is going to happen, and then we're going to hit play and see what happens. And you have a couple different options here. Is it flat? Is it going to 0 like this? Going to 0 like that? Or is it not going to 0 at all? What is it doing? Okay, you guys are going to answer that. I'm going to let my dog out, who's frantically pawing the door, and I'll be back in a sec. Okay. Okay, my wife is going to go let the dog out. Good time for any questions you have in the chat. Can we see the dog? Yeah, we can see the dog at the end of the stream, which will be pretty soon. While we do questions. Oh god. Okay, there's like 20 seconds left here. I'm gonna actually, let me see if I can get the Desmos thing open. Yeah, here it is. Oh no, did it die? Oh, that's bad. Okay, sorry if I interrupted you there. You should have another second. Oh, okay. Now there's too much time. Okay, there's only 2 people left. I think I'm going to stop it here. So sorry for the last 2 people. So let's close this up. I'm going to show you now what it looks like. So I'm going to hit play, and you'll see if you were right or not. Let's hit play and see what happens. So we're talking about this blue line over here. Actually, can you guys see the blue line? Yeah, okay. Blue is an okay color. I'm going to hit play. Let's see what happens. Oh, why isn't it working? Okay, there we go. So let's start it one more time. Play. That is what the solution looks like. So what's the answer? It goes to 0 really quickly on the ends, and then in the middle, it takes a lot longer to go to 0. So let's see what you guys said. Responses. Most people got it right. The correct answer is B. It goes to 0 starting from the ends. And you can see that in the algebra. So a few different ways. So one is, remember we had the boundary conditions that it's equal to 0 at the ends. So the endpoints immediately go down to 0. And you have these sine functions. And if you expand out what this is, if you write out this sum, right, this is how the full infinite sum, but if you write it out, you get 80 over pi is the n equal, this is the n equals 1 term, e to the minus pi over L squared alpha squared t times the sine of pi x over L. The next term is like 80 over 3 pi e to the minus 9 pi over L squared alpha squared t sine of 3 pi x over L, and so on. And so what's going on is you have this infinite sum, and all of the terms are going to 0. So the whole thing is definitely going to 0. They are going to 0. These terms are going to 0 really fast. This is an e to the minus 9 times as big as that one. So this one goes to 0 super duper fast. So what happens is all of these terms, these things go to 0 really quickly, and you're left with this is the sort of dominant term. And if I go into Desmos quickly here, let's see if I can pull this out. So this is what I want. Let me copy and paste this. Here you go. So in purple, in Desmos right now, there's two things. There's the blue curve, which is the heat, the actual bar, and the purple is just the first term. And the purple one is pretty boring. It's just a sine curve. It's a sine curve that goes to 0, so it's kind of boring. But the point is that, you know, you're watching this heat equation happen, and the blue curve and the purple curve are almost exactly the same. And that's because in the equation, all of these terms, except for the first term, go to 0 much faster than the first term. So the first term is sort of the dominant term, and you can really understand what's going on by looking at this thing. And this thing really goes to 0, but it goes to 0. It goes to 0 slowly in the middle, and like fast. At the ends, it's already at 0. So I'll go back to this. Okay, so that was the solution to this problem, and an animation of the solution. We're going to do another example on Monday and start doing the non-homogeneous things. But if you followed that ansatz method and separation of variables and how to find the C's, then I think you are good. Someone in the chat wrote, is it always the case that the first term is the dominant term? The way I've written the solution, the first term is the one with the biggest eigenvalue, the one that's closest to 0, the dominant eigenvalue, the dominant exponential here. And that term is the one that always wins. And you almost always write it like that. So that is why that works. Okay, I'm going to open this up for questions in Top Hat, but then we are done. So questions. Let's open this up. So you can put any questions in there. This is all we're going to be doing. We're going to be doing the separation of variables trick on a couple other PDEs. So today we did the heat equation. We're going to do the same thing on the non-homogeneous things and see how that works. It's going to be the same kind of like stuff we've been doing before, and so on. Okay. I'll go get the dog while you guys are asking questions. Everyone seems interested in the dog. This is the dog. Yeah. Yeah, I know. Can we see the page where you solve for Cn? Yeah, well, I cheated. I just copied it from the textbook, so I can show you the answer. Yeah. It's here. So I just said Cn, it's a chapter 10.2 problem, and it's this 80 over n pi if n is odd and 0 if n is even. Yeah, the dog is also overdue for a haircut. So, yeah. He's getting a little shaggy. His name is Pretzels. Okay, that seems to be the only question people are asking is where's the dog? So, I guess the PDE stuff is good then. Probably nobody will remember anything about the heat equation, and they'll just remember the dog, which is fine. Yeah, he's half Bichon. He's poodle and Bichon. Okay, I think I'm going to call it there. It's a good time for questions. I'm not going to tell you what happened to the painting. So, what was the majority vote on the final? Yeah, people did vote for the new scheme, so that it's like official now, I guess, or whatever. Yeah. I like his pause here. I think that's cute. Okay, so that's it. Oh, yeah, there's one more thing if you want. I'm going to open up the last Top Hat question. Is if you want, I'm going to do office hours tomorrow at some time. You can put in what time works for you. This is totally optional. So if you don't want to, don't. But yeah, so on Top Hat, you can put in what time you want to do office hours. But optional. Okay, I'm going to stop there so you can go. But if you want to leave it open for bed, I'll be here for questions. Yeah, and I'll do some Skype office hours type thing tomorrow. Okay, see you guys. Yeah, that's okay.
You know, he was asleep and he started screaming.
It's because the math was going on. He was excited by the math.
Happy he is.
There's a bonus, baby, if you stayed on the stream. Yeah! Apparently he wouldn't nap because he was interested in the math we were doing. Yeah, look, Ezra. Look at the math. Yeah. I know, it's an infinite sum. Those are hard. Yeah, we have matching haircuts, that's right. Hi. Okay, you got a nap for mom though. None of this. Okay, I'm leaving for real now. Bye.